In the last video, we talked about plane mirrors, mirrors that are flat. And most mirrors that we deal with are plane mirrors. You know, you got a full-length mirror in your bedroom, you know. You've got a bathroom mirror, say, above your sink. Those are typically plane mirrors. But we also have around us all over the place mirrors that are not flat. And they're not just in fun houses either. For example, maybe also in your bathroom you have a makeup mirror. Right, one of those mirrors that, you know, when you're far away from, if you ever tried it from far away from a makeup mirror, you're actually small and upside down. But if you get really close, of course, you're right side up, and also your face is so big you can count your pores. Right? It's just, your face is huge. Turns out that's a spherical mirror. Another version of a spherical mirror is the mirror on the passenger side of your car, where it says objects in a mirror are closer than they appear. That's also a spherical mirror. Or if you're in like a hospitals have these. If you go to one of these places where two main corridors cross in a hospital, you'll see up in the corner a spherical mirror. It makes everything look distorted, but you can see when people are coming or not coming the other direction. So there's no accidents. You know, people pushing beds and so forth won't have accidents. So spherical mirrors are everywhere. But what do we mean by spherical mirror? Well, imagine that we have some big ball, a sphere, and say that it is hollow and that it is mirrored on the outside and on the inside. So it's just like the big bean, you know, in Chicago, except for it's spherical. It's completely mirrored on the outside, and also on the inside it's mirrored. And say we cut out a little portion of that. That little portion is a spherical mirror. The outside of the sphere, where the mirror sort of bulges out somewhat, is called a convex mirror on the outside, but on the inside, where it sort of caves in like a little bowl, that's known as concave. So here we have sort of a situation like this. I don't have mirrors with me here. Should have maybe brought some with me. But suppose I am looking in a mirror here. Okay, so this is the our time-honored disembodied floating eyeball looking at a mirror from the right. So if my hand is a mirror, I'm looking at the mirror this way. Okay? First case is concave, so it's like this. It's sort of like the inside of the big glass ball. Okay? And this picture here is the convex side when it's turned this way away from me. Okay? Now this sphere has a radius r. Okay? And so in the first case, we can label a point out here, a point called C. C is known as the center of curvature. And it basically represents the center of the sphere from which that was cut out. Okay. For the convex case, the center of curvature, actually let me erase this PA, I'll explain what this PA means here in a second. Okay. For the convex case, not too surprising that the center of curvature is back behind it, right? Because it curves this way. So the center of the sphere out of which it was cut would be over here somewhere. So there's our center of curvature for the convex case. So let me actually label these here. Concave and convex. So these are important points. Now this line I've drawn across the middle is just called the principal axis, and it's just a nice reference line for us to use. We'll be drawing some angles, we'll be drawing some things called objects and some images, and we're going to use the principal axis simply as a reference line. Okay? And all that's important is that it intersects the mirror in the middle of the mirror. My little cutout piece here intersects it in the middle, and it intersects it at a right angle to the mirror itself. Okay, principal axis here, and also, of course, here. I'm not going to label it every time, but that is the principal axis. Okay. Anything else to say before I move on? Oh yes, there is one thing. The distance between the mirror and the center of curvature, this distance here, is known as R. Right? It's the same R that's over here. That makes sense, right? Center of curvature will be a distance R away from the mirror, right? The distance, the radius, I didn't draw the radius in this, right? But the radius, here's the center of the sphere, right? The radius would be right there. Same R, okay? R is known as the radius of curvature. So C is a point, but R is a distance. C is a point, and R is a distance. Let me actually keep my craving for color coordinating good here. Do it this way. R. C. Okay? Okay, so that is the radius of curvature. That is the center of curvature. I now want to share one more highly amusing fact with you. If you take some rays, we're going to shine some rays on this mirror, and we're going to say they're parallel. I'm going to draw a handful of them here. They're going to be red. Actually, this pen needs a little help. Pardon me for a second. You get this red flowing. I think we got it now. So we're going to have some rays hit this thing. There we go, that's better. If we have parallel rays that are parallel to the axis, maybe it's a laser beam coming from this way to that way. So we have some rays, some light rays coming in from the right. I'm going to draw 4 of them. There might be another one right down the principal axis, but I don't want to jumble up the picture too much. Oops, come on. There and there. So if we have some rays striking the mirror and the rays are parallel to the principal axis, they are known as, get ready for it, this red's not looking so good. It's been a while since I've used it. They are known as paraxial rays. Paraxial, right? It's a good name. Parallel to the axis. Parallel to the principal axis. It turns out that if we do that, if we have a concave mirror and we shine parallel rays onto it, they are all going to obey, of course, the law of reflection at the surface of the mirror. And they're all going to reflect back this way. That's what a mirror does, right? It reflects light. Light's going this way. It's going to hit the mirror. It's going to reflect and go back this way. But it turns out that when that happens, an interesting little phenomenon occurs. They all reflect back through the same point on the principal axis. Kind of like magic. I'm going to do it this way. I need to get this red a little more attention. They all, hold on, I need to, this red's driving me up a tree. It should work better than this. They all reflect back through a single point on the principal axis. I need to sit down and have a nice little discussion with my red pen here. It seems to not want to be cooperating, but it must cooperate. I depend on it too much. So when the rays bounce back, okay, that's kind of a confusing image, but when the rays bounce back, what I want you to notice is that they all pass through the same point on the principal axis. That point is known as F, capital F, known as the focal point. All rays that are incident, that means they come in at an angle that is perfectly, or they come in parallel to the principal axis. When they reflect, they pass back through point F. All of these rays do. And if I drew another ray right down the axis, it would reflect straight back from the direction it came and also pass through F. So it's a very interesting little point, the focal point. Convex mirrors have a focal point also. I'm not going to use my ruler this time. I think that's going to be a little too unwieldy. But suppose now that we have parallel rays striking this mirror, okay, so those are also paraxial rays. When they strike this mirror, they're going to, and I will need my ruler for this, I'm afraid. They're going to do this. There's a point here, that's our focal point here, is back behind the mirror. When they reflect, they're going to reflect in a direction such that they all trace back to F. So in this when this first ray reflects, it's going to go off in that direction. When this ray reflects, when it strikes the mirror and reflects, it's going to go off in that direction. When this ray reflects, it's going to bounce off in. This red pen is really disappointing me today, friends. And then this one here is going to bounce back down at this angle. Like that. So that if I trace these back, they're all going to land at the same point back in the world behind the mirror. They're all going to reflect back to the left. But if you trace all of these rays here, these rays that I've gotten drawn with the arrows pointing this way, so they come into the right, but then they bounce back to the left. And we're the observer. We're back here. We're looking at the mirror like this. Okay? So the rays that we see are the rays coming back this way. The rays that are going to enter our eyes are the rays that come back this way. And if we trace them back, they all seem to come from this focal point back behind the mirror. Okay. Now the focal point is a distance f, little f, away from the mirror. So this distance here, let me think of a good color to use. I'll have to use orange again. This distance here, let's use white. This distance here is known as little f. And this distance here is known as a little f. And of course, we also have r. I didn't draw r down here, but I could have. Right. Could have also drawn r there. So this length f is known as the lowercase f. So capital F is a point. Lowercase f is a length. Little lowercase f is known as the focal length. So C and R go together, and F and little f go together. C and big F are points. R and little f are distances. They have units of meters. Radius of curvature and focal length both have units of meters. They're both lengths, but C and capital F are both points. And I'm going to leave you with one last interesting, amusing fact, and that is this. For the concave case, there is a simple relationship between F and R, and that is that the focal length F is equal to 1/2 R. Okay, and in the convex case, the focal length is equal to minus 1/2 R. We will address that minus sign very soon, but basically the point is that lengths behind the mirror are negative and lengths in front of the mirror are positive. But we'll say much more about the sign conventions in a couple of videos from now. But for now, know that for the concave case, F is 1/2 R. For the convex case, the focal length F, little f, is negative 1/2 R, minus 1/2 R. Okay, there's lots of new terms here. They're all going to be used a ton in the rest of this chapter, both talking about mirrors, as in this case, and later on when we talk about lenses. So, that's it for this one. See you next time.